it's time to do a number 2. Let's just get on with it. This is the second episode in this series intended to teach you how to make your own fast slicer profiles, specifically in Cura, and this one is probably the most important. Let's go! This video is sponsored by PCBWay, more about that later on. Last time we looked at, let me get my weird mind map out, we covered line height, minimum layer time, Z-hop I think, and some other stuff, but do you know what we didn't talk about? Lots of things, but we specifically didn't talk about speed. It makes sense if you want to print faster to increase speed, right? Well, not so fast. I mean, literally not so fast. You do not have infinite speed. And how much speed you have does depend on a few things. The first one I want to look at is easily demonstrated by this Voron 0 I built. If you want to know more about that, see the link in the description if I remember to put it there. The kinematics, meaning the actual motion system of the printer on the Voron, can go really fast. Perhaps you can see what's happening though. The printer is going fast, but the print is failing. There's nothing wrong with the printer, so why is this happening? Segue to flow rate. How does a discussion of speed become a discussion of flow rate? Well, let me show you what the inside of a hot end looks like and we'll see where this goes. A hot end is made of a heatsink we don't care about in this episode, and then it's this heat break bit attached to it, which has a narrow section in the middle, and then it widens out again, but the wide part and the actual nozzle are in what's called the heat block. This heat block contains the heating element and also the thermistor, but we're not worrying about that. So this bottom part is hot, and all of it is intended to be around about the same temperature, at least in a simplistic view, not taking into account science. But the rest up here is supposed to be effectively cold, also not taking into account science. We'll see more on that in a future episode, actually. Now, it takes time to heat up 1.75mm diameter filament to the temperature it needs to be to extrude. This time is, and this may come as a surprise to you, this time is somewhat constant, at least given the same external parameters like the temperature you've set the nozzle at and the pressure. There is nothing you can really do about this. This is in fact a function of the thermal conductivity of the actual plastic you're printing. It's nothing to do with the actual mechanics of the printer. So if you're constantly printing, meaning not retracting, stopping moving, etc., you could see the maximum flow rate the hot end can sustain as a function of the time the filament is being subjected to the hot chamber of the nozzle. And you would, to my understanding, be correct to assume that. This is why volcano hot ends have longer heat chambers. In case you ever wondered why volcano hot ends have longer heat chambers, this is why. It is to increase the amount of time that the filament is heated, because increasing the amount of time that the filament is subjected to the heat allows you to move the filament through past faster and still get the same amount of heat energy into the filament, if that makes sense. And let's not forget the supervolcano. I'm not sure if we should forget it though. I don't think it is that popular. I think there's some problems with it. I've never used one personally, but if you look at the length of it, you can see that it probably can sustain quite a large flow rate. It's not very practical even, just basically, is it? Of course, recently there has been a second innovation to increase flow, and this is the Bondtech CHT solution. If you can split the filament into multiple thinner strands before it's fully melted, a bit like grating cheese, this is why grating cheese tastes more cheesy. It's got an increased surface area and a decreased thickness, so the surface area to volume ratio is higher, and that increases the performance significantly when it comes to heating it up. Why do we care about flow rate all of a sudden, though? It's demonstrated quite well here with the Voron. Back in the Ender 3 days, your kinematics were probably the limit rather than flow rate. So a nozzle with, say, 15 millimeters cubed per second maximum flow rate, which is the standard Creality hot end, give or take, would be unlikely to really be the bottleneck in most prints. But more and more these days, we're seeing printers that can hit this speed very easily. In fact, you can do that on an Ender if you push it hard enough, but usually you have to be doing something non-default profile-ish to get there. And this is the point I'm getting to for flow rate. The point I'm getting to, finally, is that you need in your slicer, depending on which one you use, to monitor or limit the flow rate if you want to print fast and not mess up. If you want to get to your peak available speed for printing, then you need to be paying attention to flow rate. In Cura, you can do this by showing the preview and picking flow rate from the drop-down to see the maximum flow rate. You can see all the flow rates, but you're generally looking at the maximum value in there. In Prusaslicer, you can do the same, but Prusaslicer actually has a max flow parameter as well, which I wish Cura had, but it doesn't so far. This is your ultimate speed limit in Prusaslicer. This is also the ultimate speed limit that you physically can't break. If you're wondering what that flow rate limit should be set to, then there are ways to test that, but luckily it's pretty easy to get a ballpark figure anyway. We literally just talked about it. A normal hot end with a normal heat chamber, so that would be a Creality hot end or a V6 or even a Creality Sprite, anything with a heat block like this turned this way, your answer is around 10 to 15 millimeters cubed per second. If you have a high flow nozzle, which might have a bigger heat chamber, it might have a longer one like the Volcano, where the heat block is literally just turned on its side, you can pretty much double the flow rate, and you end up with around 30 millimeters cubed per second. If you have a CHT nozzle, then refer to their spec sheets, but that is likely to increase your flow rate by at least 50%, I think, on top of whatever you had. Somehow, I've not actually used a CHT nozzle yet. I probably should do at some point, but it just hasn't happened. So, still before we get back to speed, we now know that our speed is limited by our flow rate, which is a function of our line height. They are all related. Maximum flow is a function of the speed you're extruding and how much you're extruding per fixed length. You can print faster by increasing your line height, you can print faster by increasing your line width, and this means less walls. If you have a fixed width, you can have one wall that's twice the width of two walls, so that's why it's faster. But if you hit the flow rate maximum limit, it is game over. You cannot go any faster in terms of extruding physical material. Finally, we arrive back at speed after that minor detour. You can hopefully see that print speed is absolutely not the only factor in printing faster. Let's do an example. I'm going to slice this model here and we'll try to aim for a fast speed. We're making our own profile here, by the way. This is how I generally make profiles. Start with the default Ender profile, slice and check the flow rate, and typically that will be very, very low. Ender profiles don't really push printers at all, so this gives you a lot of room for improvement. The first thing I would do is raise the line height, and you should be able to see an immediate improvement in the time, and you should also see a corresponding immediate increase in the maximum flow rate. Then I would probably look for a speed that doesn't break the flow rate. If I'm happy with that speed, and if I think that it's possible for the printer to do it, then I will go ahead and print it. And that is pretty much optimizing for maximum flow. If I am not happy with it, I will adjust it a bit more. If I can push a bit more out of it, I might increase the line width. And that's probably about the quickest you're going to get that part printed on that hardware. So I guess you would be able to get a decent time saving on this print here, which appears to be the word PCBWay, which by total coincidence is the name of PCBWay, the sponsor of this video. If you want to not care at all about your print times, or in fact anything really about the slicer settings at all, then you can always send your STL file over to PCBWay and get it printed by means of one of their manufacturing processors, be it resin, SLS, SLM, which can be used for metal even, FDM like this video, or if that's not enough for you, then how about some CNC machined parts in all these materials? Some you will probably recognise. POM is this stuff, FR4 is circuit board material, PTFE is, we all know what PTFE is, right? Anyway, you provide the correct format CAD files and pick the options, and they will quote and make it for you. Go check out PCBWay's website at the link below in the description, and thank you PCBWay for sponsoring this episode. So, speed. Actually, there's a bit more to speed than just print speed itself, and this would be the first derivative, and that other thing that isn't the second derivative of speed. We're not going there again. I am talking about acceleration and jerk, and how much use these are is very dependent on your hardware. On this Ender, the default acceleration is, I think, 1000 millimeters per second squared, but the default jerk is, I believe, 10. Acceleration is how fast the axis in question is allowed to speed up and slow down, and jerk is a constraint on how fast that is allowed to happen. The reason jerk exists as it does on printers is because if you didn't include it, acceleration would either have to be really slow, or you would get this. which isn't good. If you have a newer build of Marlin, or if you have Clipper, then you have things more like this to contend with. Same basic idea, accelerations, rates, square corner velocity. If I tried to explain that last one, I'd probably get it wrong or have to spend 10 minutes doing so. That is an episode in itself, but the point is that you can tune each one of these to make your printer finish printing sooner. It's quite hard to really quantify the time saving in the slicer on the adjustment of these settings, because quite often this is where the print times and the slicer estimated times start to drift away from each other. So here's two parts and their respective actual printing speeds. These were printed on the FL Sun V400, which runs Clipper. So what have we actually learned in this episode? It has been a bit rambly, but that's because the concepts here are all mutually inclusive. They all affect each other. But we can print faster using increased flow rate, and we can print faster by increasing the parameters around the kinematics. The former is very simple to get right, but the latter is probably going to need some experimentation to tune in properly. I hope this was of some help. Let me know in the comments. I think there's at least one more chapter that can be done on this with what's left over, so on that note, I will see you next time. Thank you for watching.